Let's just start. We wasted enough time. So last time we just defined epigraph. So what was an epigraph for a function? F of x. What is epi of f? And this essentially I'm adding Rn cross. Okay, and we said something about a property of epigraph being convex depending on function being convex. So any ideas how do we do this? So what we want to prove is, so this is true for any function. Now I'm saying f being convex. So here's the theorem. F is convex if and only if ap of f. See the distinction. This is a convex function, while this is a convex set. Keep that in mind. Okay. So any ideas why this is true? Somewhat strange, right? From pictures, yes. But otherwise, why should this be true? We'll get to the equations in a minute. That will tell us exactly what is going on. But any other simple interpretation that why this should be true? We saw that for level sets that was not true. Only one direction implication was true. But here, this is very strict. It's a complete characterization of f being convex. And the advantage here is that f need not be differentiable at all. Or other characterization we'll look at today will require f to be differentiable. And we also saw last time, if you take max of f1 comma f2, where f1 and f2 are convex, this gives you right away an answer that the max is also convex, where the max function need not be differentiable. So any intuition as to what is going on? I can draw the picture. So for any convex f, which looks like this, ap is nothing but this area. So now you're saying f is convex implies ap is convex, and ap is convex implies f is convex. Anything which comes to mind, why that should be true?
Left to right, it's like
I don't say left to right, just say if f is convex.
convex.
Why is f convex? What's the, I want you to come up with an intuition. Equation will tell you directly what is going on.
Sorry, why f is convex?
No, when f is convex, why should f be convex?
If, by the definition of a convex function, any straight line will lie above the graph.
Okay.
And as per the definition of epigraph, it includes all the points that are lying above the graph, something similar to that.
That is not. Make it concrete. You're right. F being convex, what do you get? Any chord lies above the function. That much you got. Why does that imply that AP is convex?
We can visualize AP to be the union of all such lines joining.
That's a strong statement. What are those lines?
Basically, we can cover that AP graph by using straight line.
What is the property of AP? What are the points included in the AP graph? Somewhere you have to use that fact, right? That it consists of x comma t, where t is greater than or equal to f of x. You're not yet using that. All you've exploited for the moment is that the chord lies above the function. But what does it have to say with t greater than f of x?
To take any 2 points in the AP graph
Okay,
and join them.
correct.
Get a line segment.
Yeah.
Now extend the line segment such that it intersects the curve as
Okay.
f of x. So once it intersects f of x, then those 2 points, like because f is convex, we would have that any two. So I need to make it concrete in my head. So like if
You can draw pictures.
Huh?
You can draw pictures in a notebook. That might help.
It doesn't have to be the 2 points. No, so you take any 2 separate points. And then they need to find separate points in the every term. Yeah. So then join there. Okay. So that line segment will have to like intersect the curve at f of x other points like it. We can project it like not interesting. Right?
It's okay, go on. Don't interrupt. Let him. He'll get stuck somewhere.
Why would it not just
Hey, go on. Why are you stuck? Think about what is the property we're trying to do. There are only 2 properties to exploit. One, that f is convex. 2, the definition of f. There's nothing else you can exploit. You're not given anything.
that's what I was talking about. Like, these any 2 points is an example.
It's okay. You're not giving a proof. It's okay. If you want me to draw something, let me know. I'll draw.
To prove that the FA graph is a convex set, we need to prove that the
Any-
different combination of any 2 points.
Correct. So any 2 points lying inside
Ah.
should also belong to.
Right.
So let's take. So let's take. Okay. Let me call it x into y1 and y2. All you have to show is that this line also belongs to x. That's all. So what is the property of y2? The t is such that y2 is a member of. So t is such that it's greater than f of x. Right? So y2 y1. Right? All I know is that t2 is greater than f of x2, t1 is greater than f of x. Now, why should these points in between lie there? That's all. So if you write the equation down, it's just trivial. But I wanted to think about what is going on. The math proof is just trivial. There's nothing there. But once you start visualizing, why should it that the f convex implies f to be convex? This is a very nice example. Everything is nice. The convex functions could be all sorts of weird shapes. So what's the intuition you want to carry back is the question. And don't think about writing that out. It's just trivial. You take the linear combination of the two, just by the definition, you get what you want. I want you to think about why should this be true. Fair question or I'm wasting time? You're free to say that this is waste of time. We can just move on.
So that's what I was asking. So like now we can extend that line. Connecting.
Okay, what will you get by doing that?
So now we have 2 points on the curve.
Yeah.
And this line, this point is a linear combination of these 2 points.
Let's just extend it. I don't see it, so let me know. Okay, here and let's say here. Okay, so I got new points.
So any point between y1 and y2 on the line segment will also be a linear combination of y tilde and y tilde, because there's a line segment joining them.
Okay.
So because now we have that f is convex, we have that f of the linear combination of y tilde and y tilde, y1 tilde and y2 tilde must lie below that. No, the f of that will be less.
No, but f of y1 tilde is not even defined. F of the first coordinate is defined.
Y1 tilde must be a.
No, you're saying y1 tilde is a member of the epigraph, right? So what is the type? X comma t.
Right.
And given that it's on the boundary, it's strict equality. That's all you get. But how does it help you? Because I can't evaluate f at y1 tilde. Sure.
So, since f is convex,
Mhm.
by definition of convex function, the f of some convex combination of x and y is less than
No,
equal
be precise. So x is the first n dimensions, t is the second last dimension, y2 is a member of my epigraph. So I can't evaluate at y. I can evaluate at x.
f of theta of x
Mhm.
1 plus 1 minus theta of x2 is less than equal to theta of f of x1
Yes.
plus 1 minus theta of f of x2.
Yes.
And we already know that f of x1 is less than t and f of x2 is less than t. So
Yes.
that combination is always greater than t. So that means that set should be convex.
No, so if you write it in this way, I agree it's a trivial answer. All I'm trying to ask is the interpretation of it. I want you to carry back something else. An intuition why this should be true. If you open the equations, you don't get nothing. Essentially, that's the problem. I'll write in one line, that proof is over. I want you to think about what is happening here.
So then doesn't there exist like x1 such that f of x1 is equal to y1 tilde?
Yeah, that does exist.
X2
Fine.
is equal to y2.
It's unnecessary, but yeah, okay. Go on.
And then like we take the linear combination of x1 and
Fine. So there is some, let's say x1
Yeah.
here. And there is some x2 tilde here and x1 tilde here, where f of x1 tilde is equal to exactly t1 here.
Right.
Okay. Now,
So then any linear combination of that, because
now these two points you're going to take linear combination. Is that what is going on?
right. So
Okay.
that,
Fine.
So we have that f of any linear combination of those 2 points must lie above f of x1 lambda x1 plus x1 tilde plus
Fine.
1 minus lambda.
Yeah. And then it's greater than t also because by their equality. Fine.
Right. So then we have the epigraph is convex. Right. That point must lie in the.
But have you taken all points inside? You only taken the boundary points.
So every point between y1 tilde and y2.
It's unnecessary, right? All of this extension is unnecessary. So you're still appealing to the equations. I'm trying you to think about the geometry of it, let's say.
Will be the maximum of a function denoting the straight line and the function at.
So here is my function. Okay. What do you want me to do?
If we have 2 points, then we just draw a straight line passing through them.
Okay. Let's say.
Yeah, the complete line.
Fine.
So now this line segment will be the maximum of the 2 functions. The
Yes.
line and the curve.
So you're saying consider just this. Is that what you're saying? Okay.
So this is a convex set.
No. I use this proof that epigraph is convex to prove that. So I can't do that. It's a circular proof that. But yeah, whatever, like But say whatever you're trying to say. Don't stop yourself. What is this interpretation of this line? You're taking essentially max of some Cx plus D, comma F. Okay, now what happens really? There are many ways to prove max of F1, comma F2 is convex. So it's not necessarily not necessarily a circular proof. Elementary ways also you can prove that max of F1, comma F2 is convex. So I'll give you for the moment that this convex. What does it tell you? For it to be not convex, what would happen? For AP to be not convex, what has to happen? Let's do the contrapositive way.
It will not connect the 2 points in the algebra, whose linear combination.
It doesn't belong there.
Yes.
So what does it imply for the function f? Given our definition.
That we are always right about the function, the linear combination does not belong about the function, then
And let's take an example here. Let's say my epigraph is of this, let's say, they are clearly not convex. What would go wrong? That may be another way to keep some intuition in mind.
So then there will be 2 points in the algebra,
Mhm.
whose linear combination is not completely in the algebra.
Correct.
Which means it should intercept the function at exactly 2 points. Exactly 2 points.
What is your-
How do we know that? How do we know that? So all we know is that there exist points which are not linear combinations of 2 other points. So what does it mean? So supposing you're interested in this one, this point, and this point, and this guy is outside. Now what does it mean?
It means the line intersects the curve at exactly 2 points.
That's not necessary. I can keep zigzagging it and
Yes, you can keep zigzagging and seeing at least 2 points.
at least, okay, fine. So
So those 2 points of the function.
At this
the
point?
function of the function is below the.
okay, it's exactly equal. There's nothing below.
Yes,
These points are- These 2 points that's all I know. Okay. Now,
Now, since this linear combination is below the function.
yes, that
function
means
is not
what?
convex.
No, let's not jump the point. So let's call this point lambda x1 plus 1 minus lambda x2. Okay, what's going wrong with this? That at lambda x1 plus 1 minus lambda x2. What do we know? That it better be below
Linear combination.
lambda t1 plus 1 minus lambda t2. But so what? What went wrong? Goes against the very definition of convexity.
I'm not getting.
What is the definition of convex function? Is it inequality this way or that way?
F of linear combination is below the linear combination.
Chord lies above the functions. What is the chord? Lambda f of x1 plus 1 minus lambda x. But you're getting the same thing here. So
It's a contradiction.
where is the contradiction? The contradiction.
Assume that F is convex, but epigraph is not convex.
Yes. So
Now we are getting F is also not convex.
no, I should have gotten greater than equal to. I'm still getting less than equal to.
Yes.
Then why is it a contradiction? That's what the definition of convexity is, right? F at this point is smaller than linear, but that's what I'm getting.
No, in this graph.
Yes.
F of that point is above.
So say above. That's what I'm getting. This inequality is not the right direction. So this is another way to interpret it. I'll do the proof and it's one line. If you just go by the pure definition of it. But it's always nicer to remember why things are happening the way it is. So maybe this is easier to understand that the forward direction we're going to prove. Okay, so let's prove it. What should I do? Take 2 points. So direction is f is convex implies AP of f. So take 2 points. Y1 equal to x1 comma t1, y2 equal to x2 comma. What do I want to do? I want to take lambda y1 plus 1 minus lambda y2 and show that that also belongs to epi. That essentially means it is of the form
X comma.
some x comma t such that t is greater than f of x. That's all I want to show. But by the fact that y1 belongs to epi, what do I mean? I get T1 is greater than f of x1 and T2 is greater than f of x. So what is this lambda y1 plus lambda y2 give me? Lambda of x1 plus 1 minus lambda x2. So how much is this? So I'm taking the first, I'm calling it the first, it's not the first, but the first n dimensions. So what can I say about this? I'm just taking the linear combination here on the first dimension. If you want, you can think of this as lambda t1. This is the linear combination over here. So all I want to show is that this is greater than f of this, right? So why is it true?
F is convex.
F is convex.
Yeah, so f of lambda is convex, lambda x2 is that.
So f of lambda x1 plus 1 minus lambda x2 is how much?
It's less than
Is less than equal to
lambda.
lambda times f of x1 plus 1 minus lambda times f of x2.
Because
And-
f of x
And what is the property of T1 and T2?
is greater than f.
So it is lambda
T1
So this is larger than the function evaluated is, so it belongs to some x comma t. Proof is one line, literally. And that's why you will not remember the proof. You will always keep going and writing. Point is, how do you visualize this? That's the point. If the function is convex, the AP is something. There's nothing, no bump like this is possible. And why you can't do that? Because f is convex. Okay, now let's do the opposite. Now AP is convex. Nice. Yes. How shall we do this direction?
is the lower boundary of f.
Sorry?
F will be the lower boundary of f.
It's a very vague thing, but I'll accept lower boundary. It's just those points at which equality happens. That's what f is. Yes. Think about epigraph of a log function. It's clearly not convex. Will tell you that if it was convex, what would happen, and given that it's not convex, what's happening? So if you wanted to make a non-convex epi into a convex epi, what exactly do you have to do? So for the log function, what is the epigraph? It's everything here. Right? Clearly not convex. Sorry.
Log is not a
If it was not, then I would. So given that this is not convex, the function is also not convex, because otherwise my theorem would be false. Now, if I wanted to make this convex, what's the minimal thing I have to do? And in the process, what would be the inverse function of that epigraph? See, from function, I went to the epi. From epi, you can not directly go to the function, but you have a rough idea what it is. So what do I need to do to this epigraph? And in the process, do something to my function.
Convexify the.
Okay, so suppose you convexify it, what will happen? You'll start essentially adding this part. And what is it doing to the function?
Making the function.
No, don't say making the function. I'm changing only the epigraph. What is the resulting function I'm going to get?
So like we can prove it like by saying that if x1 comma f of x1 and x2 comma f of x2 lie in the epigraph, then so
You're taking points on the boundary.
so if, because the epigraph is convex, it's given to us, that means that lambda.
So that proof works. Not going to dispute that. Again, that's a two-line proof. Thing is, see something. Why should something like this be true? So take a log function, look at its epigraph, not convex. Now I try to convexify. What is the consequential effect of it on the function itself? Now it's no longer an epigraph of the log function. What did it do? Don't simply say the function became convex. Something weird is the function you look now is something very weird. But what is something that one can understand from here? But in the process of convexifying it, what are you removing from the function itself? You make it more precise.
All the functional values that are lying above the chord that
Mhm.
defines any two point of reference.
So his idea essentially was that you take something like this. Your idea was to look at two boundary points, right? And given that my epigraph is given to be convex, here it doesn't appear to be convex. Pardon me for that. Something will happen. Now, given that my epigraph is like this, and I'm trying to convexify, what am I doing, really?
Pushing the boundary, we are pushing the boundary of the epigraph into the interior
Of what?
of interior of like the interior of the convex, right?
No, that's not true. Right? You're making it convex, you're progressively making it convex.
Right.
That's okay. But as in the process, this is getting pushed outwards. What effect does it have on the function? What are we removing incrementally, let's say?
function points which are above it and between the two. I mean, in a convex function, those points should be the function should be below the third column. That's what's happening.
I'm just bringing that function below the chord. That's all I'm doing. So think of the convexifying of this is to include this line inside my epigraph. And as a result, this line is getting pulled either at it or below it. That's one way to actually think about it. Why epigraphs being convex implies f is convex. Because if it was non-convex, I could make it convex, and as a result, the function will actually become convex. So this is one way of creating new convex functions. You take an arbitrary epigraph of, let's say, log function, clearly non-convex. Now start convexifying it. It will give you a convex function. A really weird, very weird function. I don't even know what kind of function it will look like. It's something to, it will keep below this line all the time. The log function, this line will remain below that. That's the function. And then it's above everything. Okay, so now let's do the proof. Hopefully the interpretation is clear. Which one?
Yeah, this thing.
This one. Okay, so function being convex, what does it mean? Really? Chord lies above the function. Now, suppose, let's do the same exercise as we did here. Suppose the function is not convex. What would go wrong? How do I make it convex? And in the process, what will happen to the epigraph? Let's do it again. So again, let's take the log function. So I wanted to make this function. Currently, my epigraph is clearly not convex. Now, as I keep changing the function, what am I doing? I'm doing the reverse process of this. That's the whole point. If I start bending it like this, all I'm pushing is pulling this towards that.
In this particular case, doesn't the convex situation make it an open convex set?
See, this is not something I want you to prove. This is something I want you to carry through. Proof is 2 lines, doesn't require any of the technical machinery. Even here, the proof will be pretty straightforward. This is all just to visualize that why should epigraph be convex if and only the function is convex. Okay, so now let's do the proof. So let's take 2 points. AP is so y1 and y2. So we know because of convexity, y1 lambda y1 plus 1 minus lambda y2 also belongs to P of f. Okay, you want to pick some particular y's or any y's? What do you want to do? So now look at the picture, which is let's come back to AP being convex. So you want to pick arbitrary y's or use his idea of picking something on the boundary? Arbitrary. Okay, we'll do arbitrary next. Let's first pick something on the boundary. Okay, what happens? I'm given that this is true. Now, how do I convince myself that f is convex? So let this be x1 comma t1 and x2 comma t2, where f of xi is equal to t. That's what I'm given. So how should I go about f of lambda x1 plus 1 minus lambda x2? What do I know about this?
It's because it lies in the epigraph.
Yes.
It should be less than or equal to lambda f of x1. Lambda t1 plus 1.
This by definition. And what is t1?
F of x1.
This is equal to lambda of f of x1 plus 1 minus lambda. Okay, now do it for not equality. Don't take points lying on the boundary. This proof will not work. Because here it needed to be that T is, sorry, what happened here?
Just prove that
It's opposite, right? T1 is greater by definition.
that T1 is greater than.
Oh, we took equality and it was okay. We can't take arbitrary points. So if I wanted to do directly for arbitrary points, what should I do? Proof is complete. And why is that complete?
Sorry,
Why is the proof complete? No, but did we take some special x1, x2 or we took care of all possible x1, x2s?
All for plus and x2.
Why?
Because for every t there is an x1 on the boundary. It satisfies the condition.
Is it always true?
We just took a random pair with an arbitrary pair of points x1, x2.
No, you took arbitrary pair on the boundary. That doesn't mean you covered every possible x1 and x2.
X1 and x2 is like saying that x comma f of x1, x2 comma f of x2, those are but x1 and x2 is arbitrary.
That's the way to think. So first fix x1, x2 and look at their corresponding equalities because there are also points included in the epigraph. Don't start with the points in the epigraph. Then you have to convince or justify that why those x1, x2s are there. So we should not be proving something for special x1, x2s. So first try with pick any x1, x2 in the domain. Look at their corresponding points in the epigraph. That will correspond to x1 comma f of x1, x2 comma f of x2. Then so I'll leave you with this exercise. You can actually do it without looking at them. Just you have to observe something. Okay. Exercise. Directly go for the arbitrary x1, x2, which is not necessarily on the boundary. So this is not really required for this. Gives you a very simple proof, but that proof is equally simple. And do see it. It's also 2 lines. Okay. So now, last time we saw the application. I'm just going to repeat it once. Application of epigraph being convex. F is convex. So one was max of F1, F2 being convex if F1 and F2 any other example comes to mind where using this property it's easy to show, otherwise it's harder to show? This is clearly one liner, otherwise you'll have to open these things up and do something. It also follows from first principles that it is convex. Is there any other example? We discussed a lot of convex function examples. Any other example where it's easy to see that the epi is convex? What about 1 by x?
Visualize it.
See, the biggest advantage of this is when functions are not differentiable. So think about a function that is not differentiable. Sorry? Mod of x. Beautiful. How else do you prove that it is convex? By first principles. That should be possible. Any other function? So real application of this is when functions are not differentiable. Because otherwise the next thing we'll do is to look at if they're differentiable, what happens. Any other function which is not too difficult, non-differentiable? not even continuous, let's say. So that you noticed so far that convex functions need not be continuous. They're not differentiable, that's easy, but they need not be continuous either. So what is the simplest non-continuous convex function?
Between 0 and 1, let's say it is f(x) is 1. And
Okay.
so assume that f of x is between 0 and 1, let's say it's maybe 0 itself. And outside it's just 1.
Domain is also just close 0, 1 for the heck of it. Oh, what kind of function is this? It's clearly non-continuous. No question of differentiability. Is it convex? Okay, how do you prove?
So here we can see that the epigraph would be.
What's the epigraph?
So
Be careful, yeah.
so between 0 and 1, of course, it will just be the whole region.
Okay.
And at 0 and at 1, it will just be the line, but this is included.
So,
Starting. Yeah.
to be a thing, but this is another way of saying that this function is convex. Okay, anything else which is more interesting? This was just a contrived function. Non-differentiable convex function or non-continuous convex function. So how many discontinuities can you create for a convex function? Is the question well understood? So suppose I tell you that the function is convex and it is discontinuous. How many discontinuities can it have? Arbitrarily many? Okay, give me example. Pictorial is fine.
So at 0 it's 0. Then at every other point it will be like
Well, that's straightforward. Because every time you change the slope, it will become concave.
we need to do.
So it has to be, the slope has to go up. The slope cannot go down. And once it has gone down, it cannot go down again. So one value you create, that ties your hands up for a long time. You cannot have another value. All of this, I'm talking loose language, but hopefully it's clear. You cannot have two values in a convex function.
Yeah, there are values and one of them will be concave.
It's not necessary that it's concave because certain functions are both convex and concave, like straight lines. But the overall function will not remain convex. Do what you want. So, can you give me a guess of what it is, the number of discontinuities? Just create, let's say you can create 2, 3, 4. Just show me any function which where you can create more than 2. So then possibly I can repeat.
this must do that to only on the endpoints
What are the endpoints?
of the domain.
Endpoints, I see.
You can jump, right, in the sense that, let's say between 0 and 1, it is like that.
Yeah.
That will be, then between -1 and 0, it is 1. Between -2 and 1, it is -2 and -1, it is 2. And
So it's not common.
yeah, that's it.
That's not a common.
That is, yeah, okay, that doesn't,
See, one valley and your hands are tied.
right.
Oh, no. Yeah, I got it. It could be.
So is that's not an example.
Which one? That's not a convex function. So you have to have a convex function. And tell me how many discontinuities you can create. Give me the example. Why are you hesitating?
So from
The worst case, what will happen is we wrong, but we'll create more.
-1 to 1, let it be mod x.
Okay, very good. All -1 to 1. Okay.
Then from 1 to infinity, take it. But here also wait. I'll have to think of it here. Like we will just need to change the slope and
No,
put
but-
it some,
But how do you make it discontinuous?
put it above like
Where?
jump like on 1 it will be like x square plus 1.
No, so then why are you taking? Why can't you keep
It,
as small as possible?
okay, so let us take a
And
straight
then-
line over there. Like
That's what you really want to do, right? So you take a slope of, let's say, give me something.
0.
Not 0, will x1. Okay. Now the next time I'll not even, but it has to be what? It has to be some, it can't be missing all of it, right? That is not going to be a convex function. You can't say that this I'm not even going to define. That's not allowed. You have to define something. You have to define over the domain. You can't say undefined. That's not allowed. So what should I do? What should I fill in here? I could potentially jump up here and then go where? So suppose I jump here. Is this okay? It's not okay because this line is out. So that's not allowed. And you can't keep it empty either. I was not planning to do this. This occurred to me by discontinuities. There's some interesting things happening. Can you create even more than 2? So you got 5. We'll wait for others. Forget about infinitely many. Just create 3. 2 we already have on the board. Just create 3 for me, if you can. So think of it this way. Suppose there are 3 discontinuities. What has to happen? Well, function remains convex. That's the way to construct. So, or rather look at one discontinuity. How does it tie your hands up? For this example here, once I jump up to 1, what can I not do to the right side of 1?
extend it like
How?
for any other point, like for any x greater than 1,
Hmm.
if we have any,
What has to be the function value?
it has to be 1 again.
No, that's not a convex function. If I do what
In
you,
that case, at 1, the function value will be available.
this is what you're saying, right? 1.
No, I was saying 0, but okay.
0, you're coming back to,
Ah,
but that also,
still,
that's,
1 will be
so what is the only possibility?
there it has to stop.
No, that's not sufficient.
You cannot define it like
Why can't I define it to be? Would anything go wrong? If I were to define the function value to take infinity outside. This is actually a standard feature of convex function. If you're defining over a domain, if you extend it like this, it remains convex. You can convince yourself.
if continuity can be at next 2 points, but differentiability we can have like discontinuity we cannot have more than
No, differentiability is very easy to. You can just keep.
increasing the
Polygon,
Sorry?
like the lower side of the polygon will have.
Yeah.
If increasing the number of sets will.
You just think of mod x. Mod x is what is so special about mod x. You can multiply a times mod x to whatever slope as a. You keep doing whatever you want. That's the point is discontinuity. People see the difficulty. And you need not confine to this nice geometry function. Any functions are okay. Who believes it's not possible? Nobody believes that it's not possible. So give me the answer. What does your intuition tell you? If not, you are able to construct. What is stopping you?
In that, what is happening is that when you construct the FA graph, like the boundary is not fully there because the function is not continuous. The boundary is not fully there in the FA.
Yeah.
So that's what we need to somehow achieve.
Possible.
You know,
But that's not a direct consequence. I wouldn't say that.
because then the boundary is there in the FA graph, that works. Then we can have as many discontinuities so long as the whole boundary is there.
What kind of function is max there?
It's not-
So we've shown that max of F1, F2 is convex. And max clearly is discontinuous. You can create things, right? So what is going on? Is it discontinuous or is it just non-differentiable?
Could be non-differentiable, but if F1 and F2 are continuous, then max is continuous.
Yeah, so it doesn't give you much. What else can we do? So who's convinced that it's not possible? Or just not clear what is going on?
The carbon current service we have proof.
No. The worst kind of people are convinced without knowing anything. You don't see on TV everything. They're all convinced. They know anything. That's not. Yeah, scientists are better, but not necessarily. They're all bigoted scientists. Okay, what is your example?
The domain is in 2 dimensions.
Okay. Fine.
My domain is a circle,
Mhm.
and in the interior of the circle, the function is 0. And on the boundary, I can just choose any points. The
Points.
function value is arbitrary, it could be anything.
Okay. So all of this inside is 0.
The function value is 0.
Okay.
And on the boundary,
So-
the function
Yeah.
any
And
values.
so essentially you're saying, yeah, on the ring, you take whatever value you want.
Yeah.
Or possibly the same. Possibly the same.
Yeah.
Doesn't matter right, what you're doing. Okay. So value is this. Inside is 0. What's going on? Is it a convex function? A greater than 0. So what does it look like? It looks like something like, how do I draw? This is essentially, so this is 0 and this is A. How many points of discontinuities? It was staring in your face. All you needed to do,
Yeah, track the person to write 2 dimensions.
Yeah.
Stay with that.
you don't have to even look at circle, right? You could just take Cartesian product,
Right.
put 0 on the surface, anything on top. So get used to the habit of creating examples. It will help you a lot. Sometimes proofs are much easier if you see things through. Okay, so I was hoping to do something. So now let's do the characterization in terms of derivatives and second derivatives. So let f. So this is my notation for first derivative, okay, C1, and C2 will be second derivative. Then f is x. If so, this is another notation. If you're not familiar, if and only if is called IFF, which is lazy to write if and only if. For the moment, let me write it if and only if for all xy belong to the domain. B f of y is greater than f of x plus this makes sense only when f is differentiable. So what is the picture of our convex function? This is the picture. What is it telling you? So let's take this point to be y and this point to be rather. Let's say this to be x. Let's do that also. Now this is nothing but this. So what is telling you that the first order Taylor approximation is actually underestimating y. So f of y. So this is where the right hand side would be f of x plus this is the direction of this point is nothing but f of x. Sorry, this is the direction. And how much are you traversing? You're traversing y minus x. So this is the supporting hyperplane going from x in the direction of the gradient and underestimates your actual function. That's all this is. Okay, so how should we prove this?
We haven't defined gradient.
You should define gradient. Really? I could, but you know gradient of a function. No?
Like
Vector gradient.
But normally we have.
Scalar, right? So not really any different. Okay, how should I prove this? Or it just directly follows from the definition?
First step, we can try and prove this way. Let's say assume that F is called.
Okay.
Let's
Fine.
try and write it down.
No, just tell me, don't do it. Doing it,
Right, think about what to write from here. Okay, so let's say that it's called.
really goes back to the definition of a derivative. You remember the definition of derivative? That's all it is. F of x plus t minus f of x divided by t, limit t going to 0. That's all the proof is. Let's do it. I don't want to spend too much time today. So let f be convex. So what do I get? Let's say xy belongs to D. I get f of lambda x plus 1 minus lambda y to be less than lambda f of x plus 1 minus lambda y. Now somehow I want to bring the derivative. What do you think I should do? Something has to be taken as some subtraction. I'm allowed to choose whatever points I want to choose. So which 2 points should I choose? How does the difference look like? So that I can think of the derivative at point x. That's what I want to think about. So I really have to make a choice of x and y's appropriately. So what if I reinterpret this as some point z? So what does it tell me? F of z is less than equal to lambda f of x plus 1 minus lambda of y. My target is to somehow get to the gradient. Think of one dimension, nothing changes. Derivative in one dimension, nothing will really change. So how much is f of? I need some difference, right? How much is f with z minus f of x?
We take the limit like f of z minus f of x by.
No, that comes later, but just look at this. From here, what do I get? I get lambda of
One minus lambda. Lambda by this.
here 1 minus lambda.
And f of y minus.
So 1 minus lambda f of y.
F of x.
Here is some lambda missing, right?
Lambda.
But something is going either wrong or kind of useless. Can somebody point out what's going wrong or is going in a useless direction? What do I want? I want gradient at x. That you should remember. And does everybody know this identity? It's not difficult to prove. That gradient of f of x transpose times w is equal to limit t going to 0 f of x plus tw minus f of x by t. If not, not difficult to show. All the what is the usual definition? There's no w here, and there's no w here.
In one dimension, we can just do it from the picture itself. Right? So what happens is that f of y, like, let's say that we have like f of y minus f of x
F of y minus f of x.
by y minus x will
Yes.
be the slope of the secant connecting x and y.
Okay.
And that must lie above
But
any
it-
linear combination. Okay,
It has to pop out from here anyway.
yeah.
That's precisely what we're trying to do. We're creating this point z, which is nothing but a linear combination of x and y.
It's like that, like it's-
Here,
you will get a gradient at x.
yeah, but combining it this way is going to create flowers. So let's combine it slightly differently. Let's combine it the following way. Let's take, because we want at a particular point x, not y, you could always substitute. So let's take z equal to lambda y plus 1 minus I still have the same inequality, right? Because this is a linear combination. This is equal to f of lambda y plus 1 minus lambda x is less than equal to lambda f of y plus 1 minus lambda. This is by convexity. So what is now? It's much easier to handle this. Now I don't have to worry about those lambdas which are getting 1 minus lambda and 1 minus lambda. Now I'll nicely get lambda f of y minus lambda f of x. So I can bring the lambda down here. That's the point. So using this identity, del f transpose x, y minus x. What is this equal to? Just by using that limit t going to 0, f of x plus t times y minus x minus f of x over t. So somehow I want this in this form. What is that? From here, what do I get? What is z? If I put lambda equal to t, isn't this f of z? Pick lambda equal to t. This is nothing but, so this is f of z minus f of x over t. And what is f of z? Is less than equal to, so picking lambda equal to t. So this is at most how much? F of y minus f of x. And what did I want? I wanted this quantity to be connected to f of y and f of x. That's all. So this is all really what we're playing. But again, keep the picture in mind. first order Taylor series under approximates the convex function. That's what really it is. Okay, so let's do the reverse direction. What do I know? That f of y is greater than f of x plus del f x. Okay, so given that you have this, you want to show that f is convex. So which point do you think you will try to work with? You have 3 points really to work with. You have x, you have y, and you have something, some linear combination. So let's again take z equal to lambda y plus 1 minus lambda x. We're doing this because this is not symmetric with respect to x. That's why you have to be careful in how you choose it. I'm not hurrying you up, right? Everybody. Okay, so now tell me, this is the only inequality I'm given. What should I do? I want to claim that f is convex. So essentially the function f, so you have these x and y's, what is it telling you? If you, I drew that function. So you forget about this function, doesn't exist. All you know is that this is true for every x and y. Then the function is above this. You're not given the precise shape. All you're saying is, I start with the x, I go in the direction of the gradient at x. How much? Y minus x. The function lies above. So this picture should tell you what to do. What do you want to show? That something in between. That's what you really want to show, right? That chord is above the function. So you take some point in between x and y and show that the linear combination here and here is above this point. So what are the good 3 points? I've already given you the hint that z equal to this. So let me draw this again. X, y, and sorry. Okay, disregard this. That's not good. Just look at this. X is actually here. So because of this, f of y is greater than this. F of z is also greater than something. If this lies in between, what is f of z greater than? F of x plus the derivative of x. X is not changing. It's just z minus x. Those 2 points are helpful. So if I were to look at this point as z, it'll give me something interesting. But this inequality is true for z also. So you could even look at evaluating at the gradient of f at z also. Because from this side, if you start here, this is also fine. Doesn't matter. You're allowed to choose the freedom of whatever points you want. Because now you have to prove that f is convex for all points. That's all you have to prove. So let's try to evaluate that. So z is that. So x, y, z belongs to D. So I can, using this relationship, I can say f of y is greater than equal to f of z plus derivative of f at z times y minus z, and similarly greater than f of x greater than right? Then nothing really. keep an eye on what we wanted to prove. Lambda f of x plus 1 minus lambda. What is the, if I take the product and add, what would happen to the right hand side? If I take lambda times this plus 1 minus lambda times this. This is easy. This becomes just f of z because both are identical. What happens to this? So let's write that lambda f of y plus 1 minus lambda f of x is greater than equal to f of z as it is plus, this is common. What do you get here?
Lambda y plus 1 minus lambda times x.
Lambda y plus,
1 minus lambda times x
and what happens to z?
minus j.
Minus z. Okay, that's correct. Now what? What is z? So,
Lambda lambda
sorry, I didn't get that. See, what do you want to prove? You somehow want to prove
that is 0.
something you want to show about this because you're already in good shape. Lambda f y plus 1 minus lambda f of x greater than, if you can show it's f of z, you're done. So why is this 0?
Because z is that is equal to lambda.
Okay. So you get essentially multiplying the gradient with 0. And that's pretty much it. So many of these proofs are actually straightforward. You just have to choose the correct points to evaluate these identities. That's all you really did. So you just made a careful choice of Z. Nothing else. Okay, so the final inequality for the day, which directly follows from here, which I believe all of you know from 10th standard, I think. But when you're trying to find a maxima or a minima of a function, what were you doing?
For differential function?
Yeah.
So we first take a derivative, find the critical form, check the second derivatives.
That's the same thing we're going to do. Now, because we're working in vectors, it won't be just second derivative, we call Hessian. That's all. So let F be C2. Everybody knows what Hessian of F is, or should I define?
Matrix with the second derivatives.
Not keep crossing it.
Yeah.
So, so D da, 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 da. N. So N is the number of dimensions in which F is over yeah of F. It's so painful to do that. So these cross terms are exactly like this. Is that okay? Now what is this? The first and the second entry. So let's, what will the Hessian of F? D over dx1, d that's what the Hessian is. Otherwise, just look up. It's straightforward definition. So F belongs to C2. Essentially, Hessian exists. Then if f is convex, or the other direction. Is positive semi-definite. That's what you will know. All eigenvalues are greater than or equal to 0. That's what positive semi-definite. Or you can call it x transpose hx is greater than 0 for all x. That's what positive semi-definite means. For all x belongs to the domain, x transpose Hessian times x is greater than. If Hessian of f is greater, then f is convex. If it becomes positive definite, it becomes strictly convex. That's only the difference will be. Okay. Okay, so how should I prove this? Given that I have the previous identity. Second order Taylor, that's like the easiest thing to do. So what would that be? F of y is equal to f of x plus, anybody remember second order Taylor approximation?
Either Hessian itself times.
No, the first derivative term.
First derivative term is the same.
Yeah. Times
Y minus.
and plus
So that will be the whole test.
Hessian times what?
Times
You can just
1 minute. Yeah.
sorry, this should be I claim you're done.
It's still Z such that.
For z which belongs to xy, you do the Taylor series approximation around it. So these things are not going to, you can just read it. Okay, so I claim that you're done. Why? What does it mean? To be positive semi-definite, this is greater than 0. So this is greater than 0. So what do I get? F of y is greater than or equal to f of x plus this, which is exactly the previous result. That if this is true, f is convex. So one line. This is greater than 0. Then result. Wrong. The gradient. Okay, I was hoping to do few more things, but let's just stop here today. Now, what we'll actually do is, now we have all the characterizations we want. We'll try to see the kind of functions we said were convex are actually convex or not.